I'm speaking something. Okay. Fine. We have time. Right? Live stream is on. Okay. Okay, folks. So let's get back from where we stopped in the last lecture. So I'm going to be today's lecturer for you. So that's me. I'm a senior PhD student in working with Professor Mutlu in Safari Research Group. So I predominantly work on microarchitecture, memory, subsystem design, with some data-driven microarchitectures. I might be showing some examples in this lecture, which you might feel interesting. Okay, so this was the reading for the last lecture also for the cache, lectures on cache. We are going to jog some memory here. Why do we need caches? Because, as we know that we need both fast as well as large memory, right? So typically these two trade-offs are kind of at odds with each other. So if you make it faster, then it becomes typically smaller, but then if you make it larger, then it becomes slower, right? So we cannot achieve, as I said, like both of these with a single level of memory. So that's why we have caches as well as, multi-levels of caches, which is then finally backed up by the main memory. So that's kind of one example memory hierarchy. Like we have multiple levels of caches, L1, L2, L3 cache, and then followed by main memory, right? And then you can think of many other forms of memory also. Let's say main memory is further backed up by the disk storage, and then in many today's commercial processors, they can be also have remote memory and many more levels, right? But as you can see that the more you go on the lower, like the farther you go away from the processor, then you have bigger capacity, but at the same time, it comes with slower access time. That's a higher latency. So the idea is that how can we make this entire cache hierarchy as fast as possible as well as big as possible, right? So recall that there are some terminologies that we had covered in the last lectures. Block is the granularity of the cache accesses that we have, right? So, and then, the cache has the concept of cache hit. When you are looking for some data in the cache, if it is already present, that's called cache hit. If it is not present, then that's called cache miss. And then we have, multitude of design decisions, which affects how the cache hierarchy is going to perform. Like some of the design decisions are like cache size, granularity of the cache management, which is the cache block size. And I'm going to show you some examples like how cache block size is going to affect the performance of cache. Replacement policy, placement policy, everything essentially determines how the cache is going to behave. Okay, so with that said, let's the goal of today's first part of the lecture is going to be finish the cache that we had started in the last lecture, and then we are going to move to some other form of let's say latency hiding techniques in the later part of this lecture. So let me start with how exactly we design the cache and what sort of parameters that we are looking at and how these parameters affect the cache performance. So performance is kind of sometimes it's hard to measure in like what would be the end-to-end workloads performance if you change any of these parameters like the cache size, block size, associativity. But the easier metric to argue is the cache hit or miss rate. So that's what I'm going to show you here. So how cache hit miss rate affects, or let's say cache size affects the cache hit miss rate. So this is one figure, like it's a very let's say industry looking figure without any numbers on the axis. So you have cache axis on the x-axis, hit rate on the y-axis. So as you can see that the more cache sizes you put in the system, at some point it won't give you any further hit rate. So that point is what we call the working set side of the workload is entirely fitting inside the cache, right? So then if you increase the cache size even more, you won't see, or let's say you would see marginal improvement in the cache hit rate, right? So that's what we are saying here, that if you have too large of a cache, then obviously you need to keep in mind that the bigger the cache, the slower it would become. But then if you also make the caches too small, then it won't exploit the temporal locality, it won't exploit the spatial locality also. Then useful data would get replaced. So then that would also, decrease the performance. So ideally what you want to do, you would want to make the cache, let's say, as big as or as small as fitting the working set size, right? So then your life is good. Then the data that the workload is touching is kind of fitting inside the cache. That's the sweet spot that we want to work on. What's the definition of the working set? So working set is essentially, you can think of it in this way, that the entire set of data that the workload is touching at a specific time interval of that workload. So the workload can actually run for a long time, right? But then we're not entirely caring about the end-to-end workload's data footprint, but then at a specific given time, what is the data access, or what is the amount of data that the workload is accessing? So that's the working set side, and then that's what we want to fit inside the cache hierarchy. Now, as you can easily guess that there is no single working set size, and life would have been much easier if that's the case. And so, as I said, like the cache size and the working set size would also vary from workload to workload. So here I'm showing some example like how that happens in real workloads, right? So on the y-axis, on the x-axis, you have the number of ways from 1 all the way up to 16. So you can think of it in this way, that the more you go on the positive x-axis, you make the caches bigger, right? And then in the y-axis, you have the misses per 1,000 instructions. So ideally, you would like to see as low as possible, right? So in this case, this is one example, and that workload is this example is coming from the paper that I'm mentioning over here. So as you can see that in this case, if you increase the cache associativity from 1 to 16, so that means essentially you're making your caches 16 times bigger. This specific workload, it does not bulge at all from the misses, right? So the misses are not going to 0. The misses are still existing, but it's not changing. So what does it mean? It means that either your workload access pattern is so that the caches are not getting beneficial, even though you have make the cache really big, or it can be the case that your workload's like working set size is so big that even a 16 times larger cache is not going to contain. So that's why you're not seeing any drop in the misses per kilo instruction. But that's one example. So there can be another example of a workload. So in this case, let's say this workload shows like decent reduction in the misses, right? So as you make the caches bigger. And then there is another type of working pattern, like work access pattern, that you can see that in this case that once you increase the cache size to be, let's say 4 times or 8 times of the baseline, then you would see marginal improvement in the cache miss rate, because it already becomes near 0, right? So that's the most type of workload access pattern that we kind of see in the workload in the wild also. So that's just to show you that there is no one single one size fit all strategy. So you need to design cache that kind of caters all different types of workload access pattern as well as workload demands, right? So that's hopefully I can convince you with this. Okay, so now let's see like what the cache's performance, how the cache performance gets affected by the cache block size, right? So as I said, like the block size is the data that is tagged with the tag itself. And in this case, let's say the block size do not necessarily need to be the minimum quanta of data transfer between the memory and the cache hierarchy. Like we have covered this in the last lecture also, that you can have, let's say, super cache block with tags inside, right? So that's what we call the sub-blocking. But in this case, like for this sake of this discussion, think of the block size itself is the minimum quanta of transfer that we are looking at, right? So that's the entire block size. So if you have too small of a block, right? So in this case, on the let's say lower part of the x-axis, then the more the cache block size that you are increasing, the more spatial locality you are exploiting from the cache, right? So you're essentially saying that, oh, I'm fetching entire 64 byte at once. So that means my anticipation is that if I'm touching any cache, any data in that 64 byte, I'm supposed to touch, let's say, some few more data in that same 64 byte. Right? So that's the spatial locality that we are exploiting in this case. So if the more you increase the cache block size, the more spatial locality you are exploiting. And then you would also expect that the hit rate would going to increase depending on, let's say, if your workload is also spatial locality friendly, right? But then if you have too small of a block, right? But at some point, the more you increase the block size, the performance would taper off. So let me justify like why is that the case, right? So as I said, like if you too small, if your block size is too small, then you won't exploit the spatial locality. You would also have the larger tag over it. So that's why the more you increase this cache block size, the performance increase that you would see in the beginning. But then once you start making the cache block really big, then you would have, let's say, you are literally probing into the extreme end of the spatial locality. So you are anticipating that, let's say, instead of making 64-byte cache block, if you make it, let's say, 2 MB cache block, right? Nobody is stopping you from making that big of a size cache block. But then you are betting on this fact that if you are touching any data in this 2 MB region, the other data in that same region is equally likely to get accessed, right? That might not be the case for every workload. If it is for some workload, then it's like you're making a correct decision. But if it is not, then you would actually see performance drop, because this huge block, it would take a lot of time to transfer. It would also waste energy. It would waste the cache space, bandwidth, everything, right? So that's the sweet spot that we want to operate on. The cache block size should not be too small of a, to exploit spatial locality, as well as it should not be too big to waste the energy and then the bandwidth also. Okay, so similarly, associativity also has heavy impact on performance, and then I guess you have seen something similar on this graph in the previous lecture. So as you can expect that if you have larger the associativity, you would expect to go the cache misses to go low, because then you would have less conflicts, right? But then at the same time, if you have smaller associativity, you would actually end up having more conflicts. You would get less access time, because now everything is quickly, you can get the data quickly, you can get, there is less comparisons to be made, which I believe that we have covered in the last lecture, right? So there are less comparisons to be made, so that kind of makes the cache architecture efficient. But at the same time, you would also see, let's say, more misses coming from the conflicts, right? So here is one, good question that I want to ask you, like, so associativity, when we talk about associativity, many of the computer architecture related parameters are typically set in power of 2. So do you believe that the associativity needs to be power of 2? Who thinks that it should be power of 2? Anyone? Or who thinks that it can be anything other than power of 2? Okay, I can see some hands over there. Okay, so the answer is correct, that you can literally have non-power of 2 cache associativity. And in fact, I'm going to show you some example that, even commercial processes that we have today, they contain non-power of 2 cache associativity. So how can you use it like non-power of 2 cache associativity from this, let's say, the architecture that we have looked at before? So if you have, let's say, like this is the typical architecture for 4-way cache associativity, right? So you have tag matching logic on the top, and whatever the tag match is, then you are going to feed that matched signal to the multiplexer. The multiplexer is going to select which the data that you should be reading from the cache ways, right? And if you want to make this cache architecture 3-way, you just simply drop one comparison. So similarly, if you have, let's say, so here I'm showing some another example of 8-way fully associative cache, right? So you have 8-way tag matching logic that gets fed into the multiplexer, and then the multiplexer selects which data block that you want to access. But then if you want to make it 7-way cache associative, you just simply drop another way. So what I'm trying to point it as that associativity is not something that is needed for, let's say, for example, indexing the cache, right? So that's why we don't need to have an artificial constraint that it needs to be, let's say, power of 2. You can literally make cache associativity anything which is also not power of 2. But the caveat is that if you, let's say, in this case, if you want to have a 9-way fully associative, then you unfortunately need to go to the next power of 2 and then reduce it down from there, right? So you need to support a 16-way associative lookup, and then you just simply get drop of the associativity that you are not using. but it's possible. So this is one example of, it's a pretty recent microarchitecture coming from Intel that's called Lion Cove. And I'm pretty sure like all the Ultra series processors you might be having laptops shipping nowadays, they have non-power of 2 cache associativity. Like, for example, this is 48 kilobytes 12-way, as well as the last level cache that this processor has, it's also for 12-way associative. So it's possible. Okay, so with that said, I'll go to some other aspects of the cache performance, right? So what type of cache misses that we typically look into in real life? So there are 3 C's in cache performance. So one is compulsory miss, capacity miss, and then the conflict miss. Okay, so let me define like what are these 3 misses. There is another C here, which is called coherence miss, which is probably I'm not going to talk about in this part of this lecture. But yeah, so essentially there are 4 C's of cache performance, but then 3 C's what I'm going to show in today's lecture. So what is compulsory miss? Compulsory miss means that you are going to touch this cache line for the first time in your life. The program is touching for the first time, so you have not seen it before. That's going to be missed, right? So unless you have any speculative technique going on, the first access to any cache line is going to be missed because it's not there. You would cache it, and then subsequent access to that cache line is going to be hit. That's the whole idea, right? So the first access is to a cache line is what we call the compulsory miss, because we cannot hide it unless we have any other mechanism, which we have. I'm going to show you in the later part of the lecture. But yeah. But then we have something called a capacity miss. So what do we mean by capacity miss? Capacity miss, as the name suggests, is that any misses that are coming from purely by the fact that the cache is not too big. Okay, so this is defined in the following way. And then, by the way, there can be cyclic definitions of these two. They're saying that okay, compulsory miss is this. We can define conflict miss, and then we can say that okay, anything that does not fall into these two categories would be capacity miss. But then I'm trying to define the capacity miss by itself. So it is defined as the misses that would occur even in a fully associative cache with optimal replacement policy of the same capacity. So it essentially says that your associativity is not a problem for this miss. So essentially, you cannot reduce this miss even if you make it fully associative, because this miss is still there even after making it fully associative, and with optimal replacement policy also. So capacity miss is truly stemming from the fact that your cache is not big, right? And then conflict miss essentially is anything that is not between these two, right? So you can think of a conflict miss as that you have, in reality, you might not be designing a fully associative cache. So that means you are making it associative. So that means once you index in the set, then only there are a handful of possibilities where you can put the data, right? If you're putting the data in some place, you are essentially evicting something out who is already there. So that's the conflict miss. Okay, so that's the 3 definitions of compulsory, capacity, and conflict misses. And there are avenues to reduce each of these miss types. As I said, like compulsory miss, it's typically not easy to get rid of it unless you have any sort of speculative mechanism that anticipates beforehand. So that's what prefetching does, which is I'm hopefully going to cover in the later part of today's lecture, is if you can anticipate that, your program is accessing, let's say, cache line A, A+2, A+4, A+6. If you look into this pattern, you can easily identify that, there is a strided pattern that is going on. So I would anticipate that if you access A+8, then A+10 is going to be accessed, A+12 is going to be accessed, A+14 is going to be accessed, and then you're going to fetch the data even before the processor demands it, right? So in that way, you can get rid of compulsory miss because those cache blocks which you're predicting, they have not been touched by the program before, right? So you are anticipating ahead of time and you're fetching it on the cache so that when the program actually wants it, you would find it in the cache. So that's what prefetching does, and I'm going to cover over there. So there are avenues to reduce conflict misses also. For example, the easiest way is to increase associativity, but then associativity also comes with its own drawback of power as well as energy. But then there are other ways for getting more associativity without even making the cache actually fully associative. Then, like some examples are here, like victim cache, randomized indexing, which is I'm not going to cover in today's lecture, but if you're interested, you can look it up. And then there is, capacity, avenues to reduce capacity misses, which essentially says that, okay, we need to utilize the cache space better. So that is directly related to how exactly we are writing our program. That's what I'm going to show next. So we as a programmer, we can reorganize, we can rewrite programs which make better use of the limited cache capacity. That's one thing. Or the second thing that as a hardware designer you can do is you can employ better replacement policy, better placement policy, so that you can utilize this limited cache capacity more effectively. Okay, so yeah, so that's with that in mind. So I'm going to just quickly touch upon that, how exactly we want to improve the cache performance. So every improvement in cache performance, they have like 3 fundamental goals, right? So we want to either reduce miss rate, we want to reduce miss latency or miss cost. So that means that the time that it takes to serve a cache miss, and we also want to reduce the hit latency, right? So the time that it takes to serve a data when it is found in the cache, right? So that's the 3 fundamental goals that we would be working on, right? So how can we do? We can reduce miss rate. We can make the caches bigger, but then you can easily anticipate that all of these let's say trade-offs, they would come with own caveats, right? So as I can show, like if you want to reduce miss rate, then it can also reduce performance if, let's say, costly to fetch blocks are kind of evicted, right? So you wanted to fetch some data, put it, then but that's also evicting some data outside. So that's if that data which is getting evicted is costly, then you have a problem, right? And then, as I said, like all of these optimizations, they are very hard to come up with that improves all of them, let's say. So that's I'm going to show like some examples of how we can improve cache performance by optimizing some of these metrics. Okay, so reducing miss rate, there are lots of avenues to how we can reduce miss rate, like more associativity, like alternatives to associativity, as I mentioned. But then there are software approaches also, and then reducing miss latency, miss cost is also, there are lots of avenues that we can do. And obviously, you as a software programmer writer, you can write better program if you know that the cache already exists in your system, to make use of the cache utilization better. So I'm going to show you some examples of how we can write programs to if you as a programmer, you know that there is cache, and then most important, like any computing system or most computing system that you are going to interact with in your lifetime, it tend to have caches, right? So if you know that this computing system has cache, then how can you rearrange your code, rewrite your code so that you can make better use of cache? Okay, so there are like lots of avenues to do that. I'm going to focus on some of these that I'm showing over here. By restructuring data access pattern, restructuring the data layout, like loop interchanging, and then some blocking. I'm going to show examples of what exactly that does mean. Okay, so first example is restructuring the data access pattern. So in this case, let's say what I'm showing over here, that you can actually write or restructure your data access pattern or the data layout in the program to make better use of the cache. So for example, let's say, so in this case, consider this example that you have stored your matrix, that the 2-dimensional matrix that I'm talking about here, in a column measure order. So column measure order meaning any element in the same column but different row are going to be adjacent to each other in the memory layout, right? So that's xi plus 1j follows xij in the memory layout. But then if you go on the row wise, then that would be far apart from the memory, given that if your matrix is big in size, right? So xij plus 1 is going to be much far away in the memory location than xij. Okay, so if you know that this is the column measure like layout that you have employed, would you write this code? Because this is what we typically write, right? So we iterate over rows, we iterate over columns, and then we do some sum, right? So would you do this, or would you prefer this, right? So if you go for the row measure access, right? So you are first iterating over rows and then iterating over columns. So what would happen is that when you go from xij to xij plus 1, right? So that's what your inner loop is doing. you are literally accessing, for memory locations that are far ahead from one another, right? Given that your arrays, the matrix is really huge. So in that case, you would see, you won't essentially get any locality out of this program. But if you just simply restructure this loop, right? So if you just make the column order traversal, then you can exploit locality from the cache itself. So that's what I'm mentioning here, that just you as a programmer, you can rewrite your code if you know that how exactly you are laying out your data, as well as how exactly you are going to access that data in the program, right? So this in this case, this is called loop interchange, but then there are lots of other compiler level optimizations like called loop fusion, array merging. So many of these techniques, the compiler can actually figure out by itself. But if you as a programmer, then it's better for to make your life easier in that case. Okay, so that's one example of how, as a programmer, we can write better code. So then there is another example called blocking in this case. So blocking meaning what? That let's say the matrix that you are looking at, or the data structure that you are looking at, in its entirety, you know that it cannot fit inside the cache. Okay, but then if you want to do computation of the entirety of the data structure, then you would need to pay the penalty of going outside the cache and then having long memory access latency, right? So the idea of blocking is that, okay, instead of doing the entirety of the computation all at once, let's divide and conquer, right? So divide the computation to sub blocks, which by itself can fit inside the cache, right? So then you can exploit locality of that entire computation. And once you're done, then you go to the next block and then do the computation over there. Okay, so that's what I just said, like the divide the walking set and then divide and conquer, right? So there are multiple names of these techniques like blocking, tiling, and if you have taken any high performance computing course or let's say GPU programming, then you would definitely know some of these techniques, right? So I'm just going to show you some examples. So this is one, let's say, example. So you have a image which is consists of multiple pixels, right? And then if you want to operate on the entirety of the image all at once, your image might not fit, let's say, inside the fastest cache out there. So what you want to do, you would essentially say that, okay, I'm going to block this image, and then I'm going to operate on a small block, do all the operations, and then go to the next block, so that at least the computations that are going inside that block is going to reuse the data as much as possible, right? So that's what I'm showing over here. So if you want to block it, so that's this is the unblocked code. If you just simply access the entirety of the image itself, but then you can also make a conscious decision saying that, okay, I'm going to block it and then access it in a block fashion. That would improve the cache utilization. In this case, let's say if it is a GPU memory, then you can have, let's say, sketchpad type of memory, which you would see reuse out of those memory itself. Okay, so this is one concrete example, which is very much contextual in today's computing system, because most of you are using on large language modeling, or let's say some form of artificial intelligence, right? So, and all of these machine learning techniques, many form of machine learning techniques internally boils down to bulk matrix multiplication, right? So in this case, this is one matrix multiplication that I'm showing over here. So you're multiplying A with a B, and then you're generating this matrix, right? So as you can see that you would access A in the row measure order, you would access B in the column measure order, and that's what you're going to give you the element here, right? So that's the whole point of matrix multiplication, right? But then if you're storing both of these matrices in, let's say, row measure, then any one of the access pattern is going to show problem in the cache access, right? So if it is stored in, both the matrices are stored in row measure, then A's access is fine because you are exploiting locality, but then B's access is thrashing, right? Because you are literally jumping from elements inside the column, which is physically laid out very far from each other, right? So what you can do, you can say that, okay, instead of doing, accessing it in the full blocked manner, right, the entirety of the matrix all at once, what you can say that, okay, I'm going to just do a partial, like block-wise computation. So instead of doing the entire matrix multiplication, you do a tile matrix multiplication for this tile itself, and you would set the tile in such a way that entirety of this, two of your source tile as well as your destination, tile kind of fits into your cache space that you have, and then progressively you would just simply forward on the tile. So at every computation, you are going to generate some partial sum, and then go to the next tile, project it there, go to the next tile, project it there. So that's what you're going to give you better cache utilization, which is going to give you better performance. So if you want to write any high performance code, these things that you need to be careful about. Okay, so with that, there are lots of other complementary lectures that we have in the online. If you are interested, definitely check out this one. So before going further, I would just show another example of how you as a programmer can, let's say, restructure your program or write better program that can give you a better performance benefit by being programmers as cache aware. So in this case, let's say you have this node structure, which is it's a linked list kind of thing. So you have a next pointer, and then think of it in this way that this is a let's say database, right? So database containing huge amount of, let's say, database of all the person in the world, right? So you have every person name and which school they're studying, and then some identifier to ID that person. So now, if you're accessing this data structure in this way, that okay, you're just simply parsing the linked list, traversing the linked list, and just simply checking that okay, if the key matches, right? So what happens in this case? So in this case, what would happen, that your node, the key property of this node, you are touching it every time, right? So all the nodes you would touch the key property, but then the other property, like the field, that the name and the school, you are not going to touch it as often as the key. Why? Because you are interested only that entry which matches the key itself, right? So in this case, like if you see that these two properties, the key and the next, is something that is very frequently accessed out of that data structure, and the other thing, the name and the school, they are not actually frequently accessed. But if you pack them together, if you lay them out sequentially in the memory layout, then you might not actually see the best performance out of the system. So what you can do, you can just simply say that, okay, we as a programmer, we know that, okay, these data points are these properties are going to be less accessed, and some properties are going to be frequently accessed. So why don't I just simply break it down into two different data structures? That's what we are going to do. So you would just simply have another data structure called node data, which would contain the properties of the node, right? And then you would just simply point the pointer from this node. So now what would happen, that you would have many of these nodes laid out one after another, right? Because instead of storing this entire 256 characters inside the node itself, now you have broken it down. So only when you're going to find a match, you would access this data structure, which is fine. Then on the linked list that you are going to traverse, it's now very compactly represented, so it can get benefit from the spatial locality from the program. So that's what another example of what you as a programmer can do to speed up your program by just writing better programs, I guess. Okay, so and then comes so this is what we talked about, how we can write better program to utilize the cache space better. So that's one aspect of, let's say, improving cache performance by you as a programmer that you want to write the program. But then there is some more things that we can do to reduce the miss latency or the miss cost that the cache is going to, the cache hierarchy is going to give it to you. So what is the miss latency, and how this miss latency is affected? So the miss latency is affected typically by two properties, right? So if it is a cache miss, where exactly is getting serviced from, right? So think of it in this way, that if it is a L1 data cache miss, then you might actually have a chance to get it serviced from L2. If it is L2 miss, then you might have a chance from L3. If it is L3 miss, then there is no other, or in a traditional architecture, there is no other cache levels present. Then you need to go and access the main memory, right? And main memory is slow. So the idea is that, to reduce the miss latency, we need to understand where exactly the miss is getting serviced from. And that dictates how costly these misses are, right? So as I said, like which cache hierarchy level that this is getting serviced from. If it is going to the DRAM, then what sort of DRAM access that we are looking at? Is it row buffer hit? Is it row buffer conflict? And we have covered some of these latencies in some previous lectures, and as you can easily understand that depending on if it is row buffer hit, row buffer miss, you might actually see different latencies out there. right? And then you also need to worry about queuing delays, like, oh, lots of requests are going to the DRAM, then or maybe even caches, then they would have queues, they would get jumbled up, and then you need to arbitrate, and then all of those latencies would quickly add up, and yeah, so on and so forth. And then today's system, when you are designing, let's say, large rack scale server class processors, right? So you're not essentially looking at only one single processor with single, DRAM chips as you normally imagine in your personal computers perspective, right? But then in real case, let's say server class, data center class processor, you have, let's say, remote memory, right? So the memory can be coming from chip, the different node, different rack, different remote server altogether. So everything kind of adds latency on top of each other, right? And then another critical point of the miss latency or the miss cost is that if it is a cache miss, how much that cache miss is actually stalling the process. And that's the moment you would start probing this question, then you would start understanding that many of the let's say assumptions that you are making might not actually hold true. So one assumption that you might be thinking that, okay, I'm going to reduce the misses and that's going to give me performance. That might not be the case always, right? So why? Because let's say if that miss is not something that is critical from the processor, if that miss is not something that is the processor is anyway waiting for, then reducing that miss is not going to be helpful. So hopefully I'm going to convince you by showing this slide. So think of it in this way. So and the positive axis on the time, so you have 3 misses coming out from the processor, right? So one miss to cache line A is completely isolated, right? So and then you would take starting from this point, you would take this much of latency to service that miss. Okay, and then there is some other 2 cache misses coming out from the same processor, but then they are coming on the same time, right? So almost on the same time. So that's cache block B and then 2 cache block C. So now if I'm going to ask you, right? So you have chance to save one of these misses, only one. So which one you want to save? Do you want to save A? Do you want to save B, or do you want to save C? Anyone? So clearly, if you see here that if you save B, you're not actually saving or you're not actually benefiting anything from the process perspective, right? Because if you save B, the processor is still going to stall for C, right? So similarly, if you save C, the processor is still going to stall for B. Apart from those few overlapping cycles, most of the cycles are kind of overlapped, right? The non-overlapping cycles you might actually save here and there, but then most of the cycles are overlapped. So saving either B or C is not going to be any important from processor's perspective, right? Because the processor is not stalling. But then if you save A, that's actually the critical one, because your processor is completely stalling. The entire latency or the miss latency is kind of exposed to the processor, right? So that's what the idea is, that so these 2 accesses, these 2 memory accesses that are happening in parallel, this is what we call the memory level parallelism, right? So once you start probing this idea that, okay, you have memory level parallelism going on, and your entirety of like the out of order processor that we have discussed in the previous lectures, right? The entirety of the out of order processor is designed to exploit parallelism, right? So you are going to execute as many instructions as possible to generate as many memory requests also as possible at the same time, right? So then if you start asking this question that, okay, so if you start asking this question that how exactly this memory level parallelism affect cache performance, or better that if you just by looking at this figure, that if you start asking question that, okay, is cache is reducing the number of cache misses is always going to give you performance benefit, or are they equally important? The answer is no. And that's what this work tries to argue, that traditional cache management policy, even the Bilaty's optimal policy that we have covered in the last lecture, they try to reduce the miscount, right? Our implicit assumption was that miscount is always proportional to performance, but that's not the case. As I showed that, if you consider the memory level parallelism, then that kind of breaks the assumption. So here I'm showing one examples, and this is a very beautiful example in this case. So think of it in this way. So you have two classes of memory accesses going on. So P4, P3, P2, and P1, these are, let's say, these memory accesses are going in parallel. So that's why I'm calling it P series. And then you have some memory accesses, which is called S1, S2, and S3, which are completely serialized to each other. Okay, and consider that, let's say your workload is completely going in this loop, right? So it would generate P4, P3, P4, P4, P3, P2, P1 in parallel, and then again it would generate P1, P2, P3, P4 in parallel, and then after some time it would generate S1, S2, S3 sequentially one after the other, and just simply going to repeat. Okay, so if that's the case, then let's consider, let's say, two replacement policy. One is the Belardi's optimal replacement policy, and another one is the MLP-aware. Let's say if we want to make if we can make the cache replacement MLP-aware. So if you recall, what is Belardi's optimal? Belardi's optimal simply says that I'm going to evict something from the cache, which is going to be accessed way further in time, right? So that's the victim candidate. So what would happen? So let's say in steady state, if you have P4, P3, P2, and P1 inside your cache, okay? So next time if your processor accesses these four, you're going to see hit. That's good. And then, Belardi's optimal is going to give you hit. So that's what I showed, that your cache state is P4, P3, P2, P1. And then you started accessing these four are hit. Life is good. Then once you go to the end of this access, right, you have the P4. Now you need to, put this access inside this cache at some point, right? So you access S1. S1 is miss, right? Because it's already not present in the cache. But now you need to put this S1 inside the cache. Which one you are going to evict? Belardi optimal would say that, okay, which one is going to be accessed furthest in the future? So out of P4, P3, P2, and P1, if you go back, it's actually P1 that's going to be accessed furthest in the future, right? So it's going to replace P1. It's going to just simply add S1 there. So that's what the cache content is going to be after you have seen the access to S1. P4, P3, P2, and then P1 get replaced by S1. Fine. Now, let's say then you see S2. Obviously, S2 is going to be a miss. But then you need to put S2 inside the cache also. Which one you're going to evict? You're going to again see out of these four, which is going to be accessed farthest in the future. Obviously, that's going to be S1 because S1, P4, P3, P2 is going to be accessed here. S1 is going to be accessed here. So that S1 is the Belardi's candidate for getting replaced. So Belardi is going to replace S1 with S2. So that's your cache content is going to be after this one, right? Similarly, if you go for S3, it's going to be miss. And then your cache content is going to be, S3 would replace S2. And then you can argue that once you come back to this access pattern again, you would see three of them are hit, which is P4, P3, and P2. But then S3, the P1 is not there. So P1 is going to be a miss, right? So you can, you do it by yourself and you can calculate. So Belardi's optimal policy is going to give you 4 misses, which is essentially 4 stalls. And that's what I'm showing over here. So that's the red stalls, right? And then that's what the timeline would look like if you have Belardi's optimal policy. Now, let's say if you have a MLP-aware policy, how does it look like? So think of it in this way that your steady state is here. So for example, let's say you have the content in the cache P4, S1, S2, and S3. Now you are going to access S1. So what would happen? Obviously, you have S1, S2, and S3. So that these 3 is going to be hit. So that's the hit. And at this point, you are going to say that, okay, if I go back, so MLP-aware replacement policy is going to say that, okay, these S1, S2, and S3 are completely exposed to the processor, right? So I'm going to save these cache blocks as much as possible. So I don't care about any of these cache blocks. I'm going to pin these blocks inside the cache, right? So I'm going to save them. So what would then Belardi would do? The MLP-aware replacement policy would do. Once it would see all of these things, it would already be there, and then P4 is going to be only the one which is over there seeing in the cache. So now with this cache state, if you're going to look into for this blob of accesses, what you're going to see that, okay, it's the P4 is going to be hit, rest 3 are going to be missed. And similarly, if you progress, because but then P1 is going to replace this, P3 is going to replace P4, P2, P1. Then after this P1, your cache content is going to be like this. And then once you access this, again, you would see only one of them would be hit and rest of them would be missed. So I'm just going a bit faster here, but if you start arguing yourself like what exactly is happening over here. So essentially you are trying to save the accesses in the cache replacement policy, which are exposed to the processor by trading off misses which are you think that it's not going to be exposed to the process, right? So in this case, what you ended up with, actually 6 misses, right? So in this case, like you can easily calculate there are 6 misses. But then these 6 misses are not happening all individually, right? So these 6 misses are only going to cause only 2 stalls because they are overlapping with each other. So that's the benefit of performance that you can see that would actually save the cycles. So that's one example of, let's say, parallelism, and how parallelism can fiddle around with your perceived notion of how the caches should work and how the replacement policies should work also. So this is one example of MLP-aware cache replacement. So some other form of parallelism is what I'm going to show quickly, and then we can go for the break. So this is the cache hierarchy that we all know and love, right? So 3 levels of cache and then memory controller. So another level of form of parallelism is the following. So let's say you know that this data is going to be missing the entire cache hierarchy, and it's going to go to the off-chip DRAM itself, right? So what would happen in normal case, you would access L1, L2, LLC, all of these caches sequentially one after the other, and then you would start accessing the main memory. At some point, your processor would start stalling, saying that, okay, I don't have any further space in the processor, and that's the performance drop that you are going to see. But then if you have some sort of speculation mechanism, that it basically says that, okay, you know what, that this memory request is not going to be found inside the cache. It's going to go to the DRAM. What would happen in that case? So you can actually say that, okay, I'm going to predict and I'm going to start accessing the DRAM as fast as possible, right? So in this case, we are starting the accessing the DRAM right after the L1 data cache access is finished. And what you can see that we are actually exploiting some sort of parallelism, right? So you predicted that it's going to go to the main memory, and you start accessing the DRAM as fast as possible. So what did you do? You essentially say that, okay, while your cache is getting looked up, this L2 and LLC caches, you actually started accessing the DRAM, right? So that's another form of parallelism which we are hiding the latency. You know that, okay, DRAM access latency is really long. So why can't I start accessing DRAM as fast as possible? So that's the whole idea, that if you can speculate, then you can go forward and access the DRAM and hide the latency. So this is one form of speculation, which again kind of save the stalls. But then, as you can easily imagine, that these things would only work, let's say, if you can speculate very accurately that, okay, this is going to miss the entire cache hierarchy and going to go DRAM. So that's something that we did, and it has some sort of flavor of, let's say, some sort of a sophisticated mechanism, which is prediction mechanism, which is kind of loaned from the machine learning, or let's say classical form of machine learning. So if you're interested, definitely check out this ones. Okay, so with that said, that's kind of let's say more everything that I wanted to cover for the cache part of the lecture. And there are lots of more prior lectures out there. If you're interested, definitely check out. So there is one thing that I wanted to just announce, that there is one like more advanced part of the cache mechanisms or cache management for the multi-core processes, which we have not covered. And once you started organizing, let's say, multi-core cache design, then coherence comes into the picture. How can you make all the copies of the data coherent with each other? How can you partition the bandwidth, and so on and so forth? So that part of the lecture, we are going to premiere it on YouTube after this lecture of today. That would be an optional lecture which you can just simply go through at your own pace. Okay. So with that said, let's get the break here, and then we would convene again in I guess 2:15. Is that good? Perfect. 22. Okay, so let's start from after the break. So as I said, like that was 24A, the previous lecture on caches 2, and this one is 24C. So that if you're thinking where does the 24B go? So 24B is essentially what we are going to premiere in the, you would find the premiere link in the course webpage. So that's something that's optional. You can, watch it at your own go. So that essentially talks about like issues in caching in multi-core systems. So that's something that, it's a separate. Okay, so with caching and everything is done, we are going to notch down a bit on a kind of related topic, but in a different domain, like a different way of reducing latency, memory latency. It's called prefetching. It's something that's very close to my heart. Okay, so here are some recommended readings, and then it's not only for let's say today's lecture, but then tomorrow's lecture also on virtual memory, so which one of my colleagues is going to cover. So that's something that you should be aware of. So as I said, like the caches and the way that we design and then discuss caches till now, we said that, okay, caches are good. We already looked into multiple ways to improve the cache performance by increasing the cache size, by increasing the cache associativity, increasing or decreasing the cache block, replacement policies, many more, right? So I just quickly alluded to it, as well as you as a programmer, how you can make better use of caches to accelerate your programs, right? But then one fundamental thing that the caches cannot solve is it cannot hide compulsory messages. So if your program has not seen that memory address before, cache is useless, right? So the first time the program is accessing it, there is no way to hide it by the cache unless you have some sort of prediction going on. So can we do better? And that's where we as an architect, we as an engineer also, we always keep asking the same question, like, can we do better? So the answer is yes. What can we do? The prefetching, right? So what exactly the prefetching is? So as the name suggests, it's prefetch, right? So essentially, we are planning to fetch the data before the program actually demands for it, right? So you anticipate beforehand and then fetch the data from the memory down the lane to the faster on-chip caches, right? So that's the whole idea. Why? Because obviously memory latency is high. I guess it doesn't need any more introduction. So if we can prefetch accurately and early enough, so like emphasize on both of these two matrices, accurately and early enough, then we can reduce or completely eliminate that latency, right? So think of it in this way that, okay, you are hungry, right? You are going back after your lectures to home and you want to eat something, right, at home. So you have two options. Either you can order after you go to home and then wait for some time to get the order delivered, and then you would eat. Or you can say that, okay, I'm going to prefetch this food, right? So while you're going back home, you ordered something on the fly, and then by the time you reach home, you would already have the food. So that's the whole idea of prefetching. Now, with that analogy, you can easily expect that, okay, if you order it much later in time, like let's say barely a couple of minutes before you reach home, then again you need to wait after you reach home, staying hungry, right? And the same time, if you order much earlier in the time, right? And let's say even when your lecture finished, maybe some of you are doing now, I don't know. So then by the time you would reach home, then it would be, it's already cold, right? So ideally you would want to do it right on the time, so that by the time you reach home, the food would be already delivered, right? So that's what prefetching is also about. You need to accurately predict, and you need to predict it on the time, so that you can eliminate or completely reduce the latency. It can eliminate compulsory cache misses, as I said. Can it eliminate all type of cache misses, like capacity, conflict, and the other C that we did not cover in the lecture with the coherence? It's just a food for thought for you just to think about, right? So what it can do and what it can't. Okay, so obviously prefetching, meaning it's a speculation. Speculation kind of involves predicting something. So in this case, we want to predict which address the program is going to be needed. And as you can expect that in many cases, it might be much easier to predict this information. Many cases, it might be even harder. So hopefully I can convince you why that's the case. So as I said, like if it really works well if the workload has predictable address pattern. Let's say you are iterating through an array, right? So if it is an array iteration, you know very well that, okay, what's going to happen next. right? Which memory location you are going to access next. But then if it is accessing much, let's say, indirect fashion, let's say you are accessing A of B of I, right? So then it might be, just jumping around. Right? So in case of irregular memory access patterns, predicting what might be demanded by processor next might be harder. Okay, so something that you need to keep in mind of that, prefetching, does it affect correctness? Like you have seen some sort of speculation, which is we have covered in earlier lectures, which is called branch prediction, right? So, and as if you can recall these lectures, that branch prediction actually very critical to ensure programs correctness also. Like if you are predicting wrong, when you understand that your predictor was wrong, you need to roll back and go to the correct path of execution. But yeah, fortunately for us in prefetching, a misprediction does not affect correctness of a program. So what would happen? Your prefetching technique is predicting some address that your program might be demanding next. You fetch that data, put it into your whatever location that you want to put it. If it is not getting demanded in the end, at very best, that at very worst, that what you did is you utilize the the communication link to fetch the data, which is wasting of bandwidth. You wasted the space where you are actually putting it. Maybe if you're putting it into the cache, then you are actually evicting some useful data, potentially useful data out of cache. So that might be causing some pollution in the cache, but it's not actually hampering the correctness of the program. And that's actually very important for prefetching, because just because it does not affect the correctness, if you are in a correct, let's say, situation when you can afford, you can actually go and make much more aggressive prediction, because you don't have to worry about the correctness of the program. So you just simply go and aggressively prefetch just for, in anticipation of improving performance. So as I said, there is no need for state recovery, and this is very much in contrast with branch prediction, or let's say another form of speculation, which I'm not sure whether we have covered, the value misprediction. But prefetching in this case is not going to affect the correctness of the program. Okay. Now, here are some basics of prefetching. So in modern systems, prefetching is usually done at cache line granularity or cache block granularity. So you're not going to prefetch, let's say, specific part of the data, like, oh, I want that 4 byte of information, I want that integer from memory. No, it does not happen like this. So whatever your cache block granularity, whether it's 64 byte, whether it's 128 byte, we typically prefetch the entirety of the cache block. Okay, so that's another anticipation that, okay, whatever you're prefetching, it's also going to be, let's say, spatially localized, right? So you would also access some of it. So that's some implicit assumption that we're making. And prefetching is a technique that can reduce both miss rate as well as miss latency. How? Let's say miss rate, you can, I hope I don't need to convince you, because if you can anticipate beforehand, when the processor actually demands it, it would actually find it in the cache, right? Because somebody already fetched the data and put it in the cache. So from cache's perspective, the miss rate drops. Why it's also reducing miss latency? Because this time that it takes to fetch the data is not exposed to the program, right? Because the fetching actually happened, let's say, behind the program's back, so that whenever the data is needed, the data is already present. So that's why it's also reducing miss latency in that sense. And prefetching as a technique, it's a very general technique, which is, it's not only applicable for the hardware prefetcher, and I'm going to show you all the like many of these examples, that but prefetching can be done by compiler itself, and many of the high performance code, the compilers for high performance code might actually inject prefetch instructions. I would be showing some of this. You as a programmer, you can also write your own prefetch instructions, saying that, okay, I'm going to access a cache array regularly. So while I'm accessing, let's say, with the element A of I, why don't I prefetch, let's say, AI plus, I don't know, AI plus 8, right? So that's the anticipation that we as a programmer can also do, so that once we want to access A of 8 would already be present in the cache, right? So that's what, as a programmer. And then there are multiple examples that we can, dig in, which system itself is also generating prefetch request. And prefetching is a very broad topic, actually. So it's not, it's equally, you would find prefetching's example in multiple cases, not necessarily inside processor, but inside your web browser also. Let's say a software which is purely running, learning from your access patterns. Right? So let's say what type of websites you are visiting, what type of, let's say, web links that you are following. It can actually prefetch web data. The idea is that you as a user, you should not be looking at the latency to load a web page, right? So as you can see, like the entirety of the concept of prefetching kind of broadly applicable to multiple aspects of today's computing systems, as well as the UI systems also. Okay, so any sort of prefetching kind of comes with 4 questions, and for these 4 basic questions that you want to answer: what, when, where, and how. What meaning, what address, and in the context of prefetching inside processor, what address that you want to prefetch, right? So what prediction algorithm that you're going to use. And I'm going to show you some examples of it. When, meaning that when you want to initiate a prefetch request, as I said, like that actually depends, that would actually impact a lot of what are the benefits that you're looking of prefetching, right? So if it is early, whether it is late, or whether it's just on time. So that's the when part. And then there are multiple questions that you need to answer is where to prefetch, right? So, and then this is a multi-pronged question. So where do you want to place the prefetch data? So you have like lots of design decisions. Do you want to place the data inside the cache itself? Do you want to place it in the prefetch buffer, like a separate buffer to put the data? Like each of these design decisions comes with its own benefit and disadvantage, right? So if you put it in the cache, then you don't have to worry about anything. Let's say, the cache is already coherent, right? So we design the cache to be coherent. So you don't have to worry about any, let's say, separate copy of the same data. But if you put it in the separate buffer, you need to, keep that separate buffer coherent by yourself. So that's a downside of putting it in the separate buffer. But then if you put it in the separate buffer, then you are also not evicting something from the cache. So you can say that, okay, even if I'm wrong, I'm not actually hampering my cache performance by kicking someone out from the cache, right? So as you can easily argue to yourself that, each of these design decisions, and the design decisions are vast, they are, every design decision comes with its own drawback as well as benefits. So this is one where. The another where is like where exactly you want to put the prefetcher to, right? So do you want to put the prefetcher in, let's say, beside L1, beside L2, beside the main memory? Like depending on where you are actually putting it, you would see different trade-offs, right? So what type of patterns that you are looking at, whether you can, train on the entirety of the memory access pattern generated by the program, or you are looking at a filtered access stream, and that affects the, the efficacy of the prefetcher itself, right? And then the how part is essentially saying that, okay, how exactly the prefetcher operates, right? So that's kind of very much, let's say, intertwined with the what part also. But then how can, how is a bit broader in a sense that, okay, are you generating prefetch request inside the compiler? Is you as a are you as a programmer going to generate? The hardware is going to generate. If the hardware is going to generate, what sort of cooperative mechanisms going on? Like, is there one mechanism? Is there multiple prefetchers? Like, how exactly that's happening? So hopefully I'm going to cover some of these, or if not all of these in today's lecture. And if something spills, my colleague in the next lecture is going to cover it in the next one. Yeah. Okay. So let's start with the what part. So what address to prefetch? As to answer this question, you first need to ask, okay, what is the trade-off, right? So, and we as an architect, we always start answering this question: what is the trade-off? So what happens if you prefetch something wrong? As I said, that it's not going to affect the program's correctness, but it's going to waste resource. What type of resource? You're going to waste main memory bandwidth. You're going to probably waste the cache or prefetch buffer where exactly you decide to put this prefetch data. You're going to waste energy consumption, right? So you literally fetch some data which is not needed by the program. So that's wasted effort, right? And ideally, all of these resource wastage that's going on for your prefetch could have been meticulously used by the demands that the program is actually generating. So always keep this in mind, that even though prefetch is not hampering the program's correctness, it's taking away resources which otherwise could have been used by the program genuinely, right? So that's the effect that you are looking at, right? So that's why we need to always keep an eye on the accuracy of the prefetching. And accuracy is essentially defined as the total number of prefetches that are used divided by the total number of prefetches that you have sent, right? So ideally, you would want your prefetcher to be as accurate as possible. So whatever prefetch that you are issuing, it's going to be used by the program, right? How do we know what to prefetch? So that's the entirety of the discussion, that And that's the ingenuity comes in. And even after, let's say, 50 years of let's say development, right, we as an architect and the researchers, we still actually invest quite a significant amount of research for developing better algorithms, right? And you can easily visualize that, let's say, machine learning is actually a form of pattern learning, right? So you can think of, let's say, how you can use machine learning to come up with pattern learnings so that you can anticipate accesses beforehand. So all of these things, I'm just giving some food for thought for you. So what sort of prefetch algorithm that you want to use kind of dictates the entire efficacy. So I'm just going to show you some basic access patterns, right? So here is one access pattern, and then in the scope of this lecture, you always, whenever you see an address, it's essentially a cache block address. It's not a byte address or anything. So this is one access pattern, A plus 1, A plus 2. As you can easily, you don't need a big brain to understand what's going on here. It's just simply streaming access pattern, right? Something a bit more complicated, but again, it's very much understandable. It's a strided access pattern, right? So it's with stride 42. So you access B, you access B plus 42. You access B plus 42 plus 42, which is for 84, and so on and so forth, right? But then I'm just making it much more harder for you to analyze coming up with a pattern, right? So in this case, let's say C plus 2, C plus 5, plus 9, 11. Apparently, if you see that, okay, that there might not be pattern, but if you see that the first, the delta between the first two is plus 2, then plus 3, then plus 4, and then 2, then 3, then 4. So if you start looking at, let's say, second degree delta, right? So it's not, the first degree delta is not constant as you see over here, but the second degree pattern repeats, right? So it's like plus 2, plus 3, plus 4, and then plus 2, plus 3, plus 4. So how can you exactly analyze this sort of pattern, right? And understand these patterns on the fly and, anticipate accesses beforehand. So all of these are essentially, let's say, the better prediction, the better pattern learning algorithms that you come up with, the more patterns that, the more accesses that you can anticipate much earlier in the future. And they can be done, like all of the commercial systems that you are using in your processors, like in your laptops as well as phones, they most likely have some sort of prefetching algorithms going on, right? So this is another form of, let's say, access pattern. So if you try to look into delta, might not be visible, but then if you look into the addresses, that address itself repeats, right? So as you can see, like XYT repeats again and again in the access pattern. So if you see whenever that, okay, X is getting accessed, you know that, okay, Y and T is getting accessed next. So that's the anticipation. And then you can literally you can construct and then see lots of different types of patterns in the program, right? So the whole, the design, the research in this direction is how exactly you come up with better pattern learning algorithms. Okay, so that's the what part. Now let's go to the when part of the prefetching. So when to initiate a prefetch request? As I said, like if you prefetch too early, the data might not be used before it's evicted from the place that you actually stored. So essentially you anticipated it way ahead in time, so that by the time it's actually needed, it's already gone. So you don't want to do that. Similarly, if you want to have a prefetch too late, so essentially you are not hiding the entirety of the latency, right? So you anticipated it very quickly, right? Very late, and so your prefetch is still getting the data from wherever the data resides, but by the time your processor already demanded it, so some part of the latency is hidden, but other part of the latency is exposed to the processor. Now the processor is stalling actually. Right. So that's ideally you would want the prefetch to happen exactly on time, right? So that's what the metric that we typically use, the timeliness metric. Timeliness is essentially saying that, okay, what part of the latency that you are hiding and what part of the latency is exposed. So you want to hide exactly the entirety of it and not, anticipate it much ahead of the time also. Okay. So as you can see, like you can make prefetcher more aggressive if you have a prefetch algorithm to identify what prefetch request is going to happen. So you can make that algorithm more aggressive, more timely by going aggressive. So what do I mean by aggressive? So if I go to, let's say, the previous example of, let's say this example, right? So if you see that, okay, there is a pattern going on B for like plus 42, plus 42, plus 42. So if you are if your program is accessing B, would you you can prefetch B plus 42, but then you would easily argue that, okay, by the time B plus 42 is demanded by the program, it won't be arriving to the cache, right? So it might be not useful, right? So what you can say that, okay, you can say that, okay, I'm going to go aggressive. I'm going to say that, okay, I'm going to either prefetch all three of them, all four of them, or you can also say that I'm going to jump ahead and then prefetch. So once you start looking at B and you know that, okay, 42 is the stride, instead of fetching actually plus 42, you would actually fetch 126. So that's like jumping ahead, right? And then from 126, you can actually start prefetching from there. So I'm going to show you some examples of how commercial processors actually make the prefetcher more aggressive by jumping ahead and then go like extract more timeliness in this case. So that's one example of exploiting aggressiveness to make the prefetcher timely. But if you have, let's say, prefetch happening by the source code itself, like compiler is injecting prefetch request, or you as a programmer want to inject prefetch request, you also want to inject a prefetch request much ahead than when you are going to access the code, right? So think of it in this way, that let's say your code is iterating through an array from 0 to 1 million, right? So if you're accessing an array element of 0, do you want to prefetch A of 1? Probably not. So you want to prefetch, let's say, A of 100, right? So that by the time A100 gets fetched from the memory to the cache, your program would actually reach to A100, and then you would need it. So this is what we are calling, let's say, you can move the prefetch instructions earlier in the code if you as a programmer or let's say compiler is injecting this prefetch request in the software. Okay, so that's the when part. Now there comes the where part of the prefetching. So where, as I said, like where is multi-pronged question. So where do you want to prefetch into? Do you want to prefetch from memory to L4, L3, L2, like different levels of caches? Do you want to, like what are the advantages and disadvantages of, putting into the different levels of cache, right? So that's, or do you want even, so this is one question that you want to answer, that, okay, if you're fetching the data to, let's say, bigger caches, then you might actually anticipating that, okay, your prefetch request, even if it's not going to be useful, it's not going to cause lots of pollution either, because your L3 cache is huge, right? But if you want to prefetch the data to all the way up to L1 cache, you are actually anticipating that your prefetch is very much accurate. Why? Because L1 is also small. So you ideally don't want to kick someone out from L1 also. Okay. So each of these decisions, they come with their own trade-offs. Where do you want to place the prefetch data in the cache itself? Like we covered this cache replacement policies in the last lecture, right? So do we want to treat this prefetch block in the same priority as a demand block, right? Or do you want to say that, okay, you know what, I have seen this prefetcher to be, the algorithm to be not that accurate for this program, so I have less confidence, so let's put it in some sort of, let's say, low confidence zone, right? So what sort of techniques that you want to do over here? So as I said, like prefetch blocks, if they are not they are known to be not needed, then you can kind of fiddle around with the LRU position, saying that, okay, I want this to be demoted, so that if you want anything to be getting kicked out from the cache, pick the prefetch one, not the demand one, right? But then you can also argue that, okay, this is one, let's say, one policy fits all is also not going to be the case, but because you don't want to go in this sort of, let's say, pessimistic policy when your prefetcher is actually very accurate, right? So there is a trade-off, right? So you want to have these sort of decisions made on the fly. So yeah, that's something that you need to worry about. Skew replacement policy, I'm not going to go too much into detail, but then the more important, another important question of where exactly you want to put the prefetcher. As I said, like depending on where exactly you are putting, you might be looking at different sorts of memory accesses coming to the prefetcher, right? So let's say if the prefetcher is physically sitting beside the L1 cache, anything that is coming out of the processor, it's visible to the prefetcher, right? And then it can mine the pattern from there, anticipate what's going to happen next, fetch it from the different levels of cache. But if you put the prefetcher in the L2, beside the L2, like it's physically present beside L2, then you are not seeing all the requests that are generated by the program, right? You're only going to see the requests that are generated by the program, but also miss the L1 cache, because that's why they arrived at the L2, right? So then you are actually looking at the request. The prefetcher is looking at those requests. So the more you would go, let's say, far away from the core, the less requests that you are going to look at. So you can either look at L1 hits and misses, or you can look at L1 misses, like if you put the prefetcher physically beside L2. If you put the prefetcher physically beside L3 cache, then it's only you are going to see L2 misses. And all of these design decisions come with its own drawback. Like the more so think of it in this way: your program is accessing lots of memory accesses, right? The farther away, the further you go away from the core, you are looking at the filtered access stream, right? So many of those accesses you won't be seeing later on. Why? Because they are actually hit by the previous caches. So you're looking at then a broken, stencil. Think of it in this way: like you're literally looking at the broken piece of data, and you are expected to make any sense out of the broken piece of data. When does it work? When it doesn't work well? So all of these things, these are something that you need to worry about when you're doing prefetching. So as I said, like the more complete access pattern that you're looking at, the potentially you are going to be more accurate, as well as you're going to cover more, right? But then it also needs, the prefetcher needs to be looking all the accesses, so that kind of makes the prefetcher design itself more intensive, right? But then if you go and this is that figure, right? So if you go further away from the core, then you are actually looking at filtered access stream here. Let's say if you put the prefetcher over here, then you are not literally going to see any accesses that is generated by the program unless it comes at this level, right? So that's a filtered stream. But then you're looking at the broken piece of information, then you need to make better sense out of it, and so on and so forth. Okay, so that's what all multi-pronged design decisions that you as an architect you need to decide before having all of these techniques inside. And as I said, like prefetching is not only something that is happening inside processor, but any sort of design systems can actually make use of prefetching. So this is one example that I'm saying that, okay, let's say your CPU is backed up by two different types of memories. One is DRAM and another one is a phase change memory with different characteristics. You can also employ prefetch mechanisms that moves the data back and forth between these two memories without even processor demanding it, right? So that when the processor demands it, you would get the data right place at the right time, right? So that's the whole idea of prefetching in this case. And you can easily extend this idea to, let's say, rack scale computers, right? Like when you have let's say server class machines, let's say in data centers, right? So you have local node, and then you have some remote node, and you have some program that is working on this compute node here, and the data actually resides in the remote node. So what you want to do, you want to pay the penalty when the data is getting demanded, it's getting fetched? Probably that's one way, but the other way is you can actually anticipate and fetch it beforehand, right? So just to motivate that, the prefetching is a very broad concept that kind of transcends to multiple application domain. Okay, so I'm just going to quickly go through the how part, which is the most interesting part of prefetching, like how exactly we can anticipate like what going to happen in or what's going to be needed by the program, right? So as I said, like it can be done by software, it can be done by hardware, and then there is a third class of prefetcher, which is called execution-based prefetching. And I'm going to, if the time permits, I'm going to go quickly through those also. So software prefetching, what does it mean? It essentially means that your ISA, the x86 or ARM, whatever ISA that you're looking at, it has some sort of prefetch instructions. And it's the responsibility of the programmer or the compiler to use this prefetch instruction to explicitly prefetch information, right? So it typically works very well when you have regular access patterns, like as I said, like maybe you're going through array and iterating through an array. That's a very naive description of a regular access pattern, but you can make use of software prefetching in other aspects also. Then comes hardware prefetching. Hardware prefetching meaning that we as a software developer, or let's say the compiler is probably not generating anything, but the hardware itself is generating prefetch request transparently. We don't it's completely hidden by the programmer, right? So it memorizes, it tries to mine patterns from the accesses that it has learned. learning accesses, strides, everything, and then it generates prefetch. Automatically, it fetches the data from, wherever it resides to the faster memory. And then, as I said, like it's a execution-based prefetching. Execution-based prefetching is a kind of different class. Why? Because it can actually be implemented both using software techniques as well as hardware techniques. So think of it in this way, that you have a program that is actually executing your code, right? And then you have a thread, and whatever that thread is, and then that thread is, it's broadly defined in multiple ways. So that thread is kind of acting as a pathfinder to your program. So it kind of runs ahead of you. The whole point of that special thread is to do prefetch for you, right? So that's the whole idea of execution-based prefetching. And it kind of fascinatingly works well in most complex cases where you cannot literally find any patterns inside your program itself, right? So if you look at the raw memory access stream, you try to find all sorts of pattern mining algorithms, you cannot find a pattern. So the option that you kind of rely on then is that, okay, what if I have a scouter thread or a pathfinder thread that kind of runs ahead of you, right, in some aspect, and it would generate the prefetch request for you, so that once your program follows through, it would actually see everything already prepared for you. So I'm going to show some examples of that. Okay, so let's start with the software prefetching. I'm just quickly go through like how x86 handles software prefetching. So this is one example of some prefetch instructions. Different, the x86 has different prefetch instructions with different hints. So that's what we call prefetch T0. T0 is one hint, T1 is another hint, and then T2, and then NTA. So different hints, and then you can read through this description. So essentially, it's different. So you as a programmer, if you use different instructions for prefetching, specific instruction with a specific hint essentially tells you where exactly, or tells the processor where exactly to fetch the data. So if you say that, okay, if it is T0, you are confident in some way, and you want to prefetch the data to some cache level. If it is as opposed to, let's say, prefetch T2, right? And then there is called prefetch NTA, which is it's called non-temporal. It's saying that, okay, I want the data, but don't put it in the cache. So lots of various possibilities are there, and we as a programmer, we can explicitly write these instructions, as well as the compiler can also generate this instruction on our behalf. Okay, so that's what the software prefetching kind of works. And I'm not going to too much detail into software prefetching. There are other pointers in this lecture, so you can just go through it. And then let me quickly go through some example hardware prefetching, right? So a very primitive form of hardware prefetching can be called stream prefetching. So what does the stream prefetching does? And this is coming from IBM's Power 4 processor. How many of you know that IBM has a Power series processor? Anyone? Okay, I can see one hand over here. Okay, so IBM, yeah. So these processors are kind of, let's say, like a user grade processor. So at some point, Apple used to have their MacBooks using IBM Power processors, and then they switched to Intel as their processor vendor, and then now they're designing their own chips. Okay, so this is one example of prefetching in IBM Power 4 processor. So what it does, it says that, okay, so your processor is sitting over here, right? So that's the core, and then you have the data L1 cache, and then L2 cache, L3 cache, and L4 cache. So what it says that if your processor is accessing, let's say, L0, L1, so think of it as a cache line, right? So cache line 0, cache line 1. So if that's the case, then the prefetcher, which acting on your behalf of the program, the moment it would say that, okay, L0 is getting accessed, it would actually fetch L1 from the L2 to the DL1 cache. Okay, so that's a front that it's maintaining, one cache line front, that the prefetcher that is sitting here is going to feed the data to this cache level. Okay, then there is another prefetcher which is sitting at let's say L2, which is saying that, okay, you know what, the moment I would see that, okay, L1 is getting prefetched from the core, then I would actually start. So it's a bulk of 4 cache lines. It's maintaining a 4 cache line front, right? So it would say, okay, I'm going to prefetch the next 4. So which is, let's say, L5, L6, L7, L8, the entire blob of it to the L2 cache. So that's like a 4 at once, right? So I'm going to do 4 prefetch requests. Okay, and then there is another prefetcher which is sitting beside L3, which actually runs 4 of these 4 ahead, right? So that's like 16 cache lines ahead. It's simply saying that, okay, L5 is getting now fetched from L3 to L2. So I'm seeing L5, I'm actually going to fetch L17 to L20, the entire 4 of it from the main memory to the L3. So what it's essentially doing is like it's creating a front ladder, right? So your core is actually only accessing L0. So core is very naive, right? So it's just accessing L0. The prefetchers themselves already primed themselves saying that, okay, core access L0. So I'm supposed to fetch the entire blob of it to L1 now. And somebody down the hierarchy at L2 would say that, okay, I'm going to fetch another blob of it from L3 to L2. And someone from beside L3 is going to say that, okay, I'm going to fetch another blob, right? So it's essentially maintaining a fetch front. The more the code goes, the more the prefetcher also runs ahead. So that's the whole idea of this sort of prefetcher. So this is a very beautiful paper on stream prefetching. If you're interested, I would definitely recommend it. And this is kind of, let's say, where it all started, right? So, and then as you can see over here, and why we actually show this thing at that time. So this is VAX 11780. How many folks know this processor? I'm pretty sure that, okay, you're okay. I'm impressed. Yeah. So I guess we are pretty, even I'm pretty old for this, young for this, I guess. But okay, so what this paper says that at that time also, if you look into the missed cost, in terms of cycles, so the more we go and in terms of cycles, and the more we go in terms of instructions. So if it is found inside the core, that's one thing. If it is going in the cache, and if it is going beyond, and they're actually, sorry, in this case, my bad, I'm just retracting. So they're essentially projecting for the future generation process, saying that, okay, the more you would go towards future generation process, this latency gap is going to be even higher. Why? Because you are making your processor much faster, right? So the faster you're accessing on the instructions, your memory is not getting any faster, right? So that's the gap that it's getting larger and larger, right? So that's what they anticipated, that, okay, current generation, it's only, let's say, 6 cycles, right? So that's the 6 cycles that the cost of it. Why? Because your cycle was also big at that time. Okay, but then if you make the processor even faster, that's what WRL Titan, then you would actually you are looking at 12 cycle latency fetching something from the DM, the memory, wherever the data resides, right? In future generation processor, that might actually go to 70 cycles. Nowadays, it's actually going into, any guess how much it can be? Is it 70, more than 70, anything? It's actually lying somewhere, depending on, I mean, obviously, it depends on what, let's say, processor frequency that you're looking at, or what sort of fast memory that you're looking at. But it's safe to say that it's much higher than, like, let's say 70. It can go as bad as, let's say, like 500 cycles, right? Which is a huge amount of cycles. So this paper kind of anticipates it's much ahead of any time, and if you can see that that's coming from 1990s, so it's transcending from 30 years down the line, right? So that's what this is. 40 years. Wow. Okay. So with that said, like there are some prefetcher performance metrics that we want to introduce, like accuracy. I introduced it before, which is you use prefetch divided by the send prefetch. Then coverage. Coverage is essentially how many prefetch misses, like how many misses that you have prefetched successfully divided by all misses. So 100% coverage means that all the misses that were happening, if you don't have the prefetcher, is now completely covered. So that's the coverage. And the timeliness is essentially saying that, okay, how many on-time prefetches that you have divided by the total number of used prefetches. So that's the first order metric that we care about: accuracy, coverage, and timeliness. And then you have the second order metrics like bandwidth consumption, cache pollution, which I kind of alluded to, that what happens in these metrics are also important. Okay, so here is another example of stride prefetcher, which I'm probably not going to go too much into detail, but the idea is same as let's say a bit more sophisticated than the stream prefetcher. But then the idea is that, okay, if you can anticipate it's with a stride n, then you are going to prefetch with a stride n, right? So the idea is that, okay, you record the stride between 2 consecutive memory addresses. If you see that there is a constant stride going on, then you would anticipate based on that constant stride, right? So this is one implementation. So if your program is generating one specific load instruction is generating this memory request, you just hash it with that load instruction. You would say that, okay, what is the last address that I have seen? What is my current address? So yeah, I'm going to just subtract with my last address. I would get a stride. And I also have, stored the last stride. I'm going to match the current stride with the last stride. I'll check that, okay, if the current stride matches with the last stride, if that's the case, then I'm going to increase the confidence. If not, I'm going to reduce the confidence. And if it gets high confidence, then I'll say that, okay, I'm very much confident that any future load addresses coming from that specific load instruction, that specific load PC, is carrying with that same, let's say, stride, right? So the moment you would detect a stride, the moment you would start prefetching. But as I said, like, timeliness can be an issue. So you want to make the prefetch request also at timely. So a potential solution can be, you look ahead into the stream, right? So if you're seeing A, then you are going to predict, let's say, A plus N, A plus 2N, A plus 3N, A plus 4N, and then so on and so forth. Okay, so that's one implementation of stride prefetcher. Then some other implementation can be also memory region-based stride prefetching, which I'm not going into that much of detail. But then stride prefetching is also something that is very much well integrated into like recent processors. Also, like any type of like ARM processors, x86 processors, they have one form of stride prefetching already happening inside the first level of cache. Okay, so that's one paper. This is another paper from Intel. It's quite old, but then Intel has also recent papers, and an ARM also has open source informations that kind of alludes to the same thing. Okay, so with that said, like, there are ways to do even more complex access patterns. So let me show you one example. So this is one example, right? So this is the stride, the delta between two consecutive accesses, right? So as you can see that, if you look into it by itself, it's kind of looking haphazard. But if you try to look into more closely, you would see that, okay, a sequence of deltas repeat, right? So in this case, let's say 7 followed by -6, followed by 12, followed by 6, -5, and so on. So that entire pattern repeats. So how can you design, let's say, this sort of, how can you design prefetchers to analyze this sort of predictors? So the idea is like, you, instead of just simply learning one stride, you would actually learn, let's say, a history of stride followed by another stride. So let me give you an example. So let's say, I'm going to store history like this. So if you see delta of 7 followed by -6 followed by 12, that kind of predicts the next delta to be 6. Right. Similarly, if you see -6, 12, 6, that followed by -5. How can you use this sort of information to predict? So you can simply say that, okay, whenever you have seen, let's say, 6, 7, -6, and 12, you actually make a prediction of 6. That's going to be your next delta. And you have some sort of confidence saying that, okay, I'm 85% confident that that's going to be your next delta. So you add this, +6 stride to the current address, issue the prefetch request. But then you can easily anticipate that, okay, this might not be timely, right? So you need to go ahead in the stream to extract timeliness. How can you go ahead in the stream? You can say that, okay, use 6, the predicted value, as if that it actually occurred, right? So you bootstrap. You say that, okay, if you had 7, -6, 12 as a previous history, if you add 6 as a current, so what becomes a current history? It's a sliding window, right? So that becomes 6, 12, and -6, 12, and 6. You look up the table, you say that, okay, if that's the pattern, what would be the next delta? The next delta is -5. So you said, okay, I'm going to issue the prefetch request for this also. But then you can also keep measuring, saying that, okay, this prediction, this correlation is 70% confident. So what is the total path confidence? You were initially 85% confident, now you're 70%. So now you're actually operating on that path to be 60%. So you're giving a 60% bet that, okay, you are on the correct path, that this is what the program is going to need. You can keep on doing the same thing till, let's say, your cascaded confidence ratio actually drops and to a predefined threshold, and then you would stop. So this is one example of how you can actually look ahead much into the future, and just by bootstrapping predictions with your own and make timely predictions. Okay, so with that, I would probably close today's session from here. Tomorrow we are going to cover a rest of the prefetcher, which is we are going to. It's a shame that I cannot cover this because this is my own work, and it's going to, my colleague is going to introduce this prefetcher to you. Just food for thought for you is that how, because prefetching is fundamentally a pattern learning problem, how machine learning can help in this case. So this is one form of machine learning that we are going to cover, reinforcement learning, and there are many more over there. Okay, so that's all of it. If we don't have any other questions, then let's close the lecture for today. Thank you very much.